Welcome back, everyone. I'm sorry that I haven't been able to upload a video recently. It's been a very busy week for me, but I should be able to get back to uploading every other day or so from now on. Today, though, I want to talk about optimization, or how derivatives can be used in real life scenarios. Now, we've been talking about derivatives and how they work in a theoretical sense with all these different functions, but what the heck could any of this mean when it comes to actual real-world problems? To begin, we'll talk about what a derivative means in a real-world context. Consider this. I throw this pen in the air. At any point in time, it has a certain height above the ground. So we can model that where if this is the graph of position versus time. It starts here, it gets higher, and then it falls down. Easy enough to understand. Its velocity, well, initially it has a positive velocity, so we have an initial point here. At this value of time, its velocity is 0. It's not moving up or down, it's at the apex of its motion. So there the velocity would be 0. And then here it gets more and more negative. So we can say that the graph of the pen's velocity would look like this. Now what about its acceleration? Well, the only thing accelerating it is gravity, and gravity is a constant acceleration, 9.81 meters per second squared, and so it's just a constant graph, and -10 is like a lot, so maybe it's like all the way down here. So that's what the acceleration would look like. Now here's the thing. We can consider this as f of t, this as f prime of t, and this as f double prime of t, the second derivative. What a derivative is saying is the instantaneous rate of change, or in a real-world context, just an object's velocity. As we see, f of t is just position, and so the rate of change of position is velocity, and the rate of change of velocity is acceleration. So now we can have an understanding for what derivatives mean in a real-world context. And then now I'm going to present a situation where you can use a derivative to solve a real-world problem. First, I want us to think about what exactly it means when the derivative of a function is 0. As we saw in the pen example, when it was at the apex of its movement, the derivative was 0 because it wasn't moving up or down. What this means is that when the derivative is 0, the motion, or the position, is at its peak, or if it goes down and comes back up, it's valley or trough. I don't really know what I would say here. But what that means is that we can find all of the local maxima and minima of a function by using the derivative and finding where that derivative is equal to 0. Now, there's a lot of situations in the real world where you would want to minimize or maximize something. You want to maximize your profit margins, you want to minimize waste, and there's a lot of applications for what's called optimization, which is going to use derivatives to solve these problems. Here's a pretty famous and standard example of optimization. Say we need to build 2 corrals for cattle, right? We have, say, 250 feet of fencing, and we need it to be in this format, a rectangle with 3 equal length divisions, right? We have the outside and then the dividing of the 2 corrals. So we can say that if the whole fencing is 250, then 3y plus the 2 x's, so 2x, equals 250. Now the problem we want to solve is how can we use this amount of fencing and this format to create the maximum amount of area of space. Now, to find the space, we know that it has to be x times y as the space of the entire rectangle. So we have area is equal to x times y, and we are going to be maximizing area. We're going to begin by using our fully known equation by finding y in terms of x so that we can plug that into our area equation. So we put it up here, 3y plus 2x equals 250, minus 2x, divide by 3, and we've isolated y. You plug that in for the y here in the area equation, you get x times 250 over 3 minus 2/3 x. And so you multiply the x out, and you get that the area is going to be equal to 250 over 3x minus 2 over 3x squared. Now, here's where the calculus comes in. We have a in terms of x, so now we take the derivative of both sides with respect to x. So dA dx is going to be 250 over 3, because the derivative of ax is just going to be a, when a is a constant. And then minus, and this is going to be the power rule, x squared becomes 2x, and then times this constant, so it becomes minus 4 over 3, and then just x instead of x squared. Now, what we want is for the derivative to be 0, because that will represent a maximum of the function a. So we set 250 over 3 minus 4 over 3x equal to 0. We can get rid of the over 3 and then also divide both sides by 2 to get 125 minus 2x equals 0. So 2x equals 125. And finally, x is equal to 62.5. Now we're not done, because this is just the x value. Remember our original equation. Our original equation is, of course, 3y plus 2x has to equal 250. Plugging in our 62.5 for x, we get that 3y plus 125 equals 250, 3y equals 125, and finally y equals 125 over 3. So this is what the real life setup for the corral would look like. You would have one side of it being 125 over 2 meters, say, long, and then 125 over 3 meters wide. And this would get you your maximum area. You can fit the most amount of cows, or whatever it is, if you use these dimensions with 250 meters of fencing. So this is how derivatives can be used to solve a real-world problem, right? This is an important question to answer, and it can be applied to many more things than just corralling cows. So hopefully you enjoyed learning about optimization, and thank you so much for watching.